In my last video, we learned how to make and read a digraph, basically mapping out which tasks depend on which. Now, let's put that to work with something called the list processing algorithm, a simple but surprisingly powerful way to schedule tasks across multiple processors. We'll make two quick assumptions. Once a processor starts a task, it finishes it. There's no interruptions. And no processor sits around doing nothing if there's a task ready to go. These assumptions might not always be realistic, but we make them here for the sake of simplicity. Imagine you are an up-and-coming filmmaker and your very first project is finally in the works. And by up-and-coming, I mean you just started and you have absolutely no idea what you're doing, especially when it comes to scheduling. You have your script ready to go, but there are still 8 big tasks before you can call it done, and you know roughly how long each one should take. Let's label those tasks T1 through T8 and map out the digraph based on what tasks can't start until others finish. The list processing algorithm starts with something called a priority list, which is just a ranking of how important each task is to us. As a first-time filmmaker, you make the priority list based on what you want, not what the project actually needs. Maybe you put submit to film festivals at the top because it sounds exciting, but logically, that task doesn't depend on anything. It's purely just what you want. In this case, T8 is at the top of the priority list, then T7, then T6, and so on until T1 is at the bottom. Then we follow one simple rule. At any point in time, pick the highest priority task that's ready, meaning all its prerequisites are done, and give it to the lowest numbered free processor. Let's say we have 2 editors, Alex and Blake. These are our 2 processors in this situation. At time 0, the ready tasks are T1, T7, and T8. According to our priority list, T8 is highest, so it goes to Alex. T7 is also ready, so it goes to Blake. Blake finishes his task before Alex finishes hers, so he starts to work on T1, the only other available task. But when Alex finishes her task, she has to wait for Blake to finish before picking up T2. They keep going like this until everything's done. The total time is 32 hours, still 15 hours faster than if just one editor handled everything alone. But as you probably noticed, there's a ton of waiting around. This is mostly because of how the priority list was set up. If we rethink which tasks actually unlock others, it's easy to see that T1 is the key that opens up most of the workflow. So let's simulate this project again, this time with this priority list. Now they finish 5 hours faster just by changing the order of tasks. And here's the cool part, we can actually prove that this schedule is optimal. Remember from my last video, the critical path, or the longest string of dependent tasks in this specific scenario, is T1, T2, T3, and T4, with a total length of 27 hours. This means that the fastest possible completion time for this project is 27 hours, exactly what we achieved. This is just a small-scale example, but zoom out a bit. Construction companies, hospitals, and even airlines face hundreds of interconnected tasks. A non-optimal schedule can waste countless hours and dollars built up over time. Next time, I'll show you how to build better priority lists by finding the critical path and working backwards. Thanks for watching.